So in this video, I wanted to go over homeostasis a little bit and talk about the parts of the homeostatic mechanism. So homeostasis is basically your body's ability to maintain a stable environment internally, even though there's things constantly changing outside all the time. So one prime example of this is your internal body temperature, right? Everybody knows that your body temperature internally should be around 98.6 degrees Fahrenheit, or in Celsius, that's around 37 degrees Celsius. You should maintain that body temperature at all times, regardless of what the temperature is outside, right? You could go outside and it's 106 degrees, and your internal temperature should still stay at 98.6. You could go outside and it'd be 30 degrees, and your internal temperature should stay at 98.6. And the way that happens is your body has mechanisms to keep it at that temperature, right? You think about, you go outside and it's really cold, and say you don't have a jacket on, what's one of the first things you start doing? You start shivering, right? Your teeth start chattering. Well, shivering is your body's way of trying to warm you up. When you shiver, your muscles are contracting, and that helps produce heat to warm you up, okay? And just the opposite, if you go outside and it's really hot outside, you start shedding clothes, right? That's the first thing. And what will your body start doing to help cool you off? It'll make you sweat, right? When you sweat, the sweat pulls up on the surface of your skin, and then the sun will cause evaporation of that sweat. And when the sweat evaporates off of the skin, it pulls heat away from your body, and that helps to cool you back down. Okay, so those are a couple of examples of homeostatic mechanisms in place within your body to help you maintain a stable body temperature inside, regardless of what the temperature is outside. Okay, so when you look at the parts of the homeostatic mechanism, the best way for me to illustrate this is to use a real world example. So not necessarily something that's happening in the human body, but something that, everybody kind of understands how it works. Okay, so the example I use is an air conditioning unit, okay, the thermostat. So what happens if you set your thermostat to 70 degrees Fahrenheit? You set your air conditioner to 70 degrees. If you come in and your temperature in the house goes up to 72, what do we know the air conditioner is going to do? It's going to kick on, right, to help cool the temperature back down. And that house will start cooling down. The AC kicks on, starts getting cooler, and it will cool down until the temperature reaches 70 degrees. And then what happens? The whole thing shuts off, right? So that's an example of homeostasis as well, helping maintain a stable temperature within the house, okay? So I'm going to go through the parts of the homeostatic mechanism while using the thermostat and the air conditioning unit as my example, okay? So in this example, the stimulus, okay, the stimulus is the thing that causes change, okay? So the stimulus in this example, this is the change in the environment that is happening, is going to be an increase in temperature, right? An increase in temperature in the room. So say our temperature goes up from 70 to 72 in the room, that's the stimulus, change in temperature, okay? The receptor is the structure that is going to detect that change. So in this case, the receptor is going to be the thermometer. Right? The thermometer found in your thermostat is constantly checking the temperature of the room, and if it notices that the temperature is too high, then it's going to send an input signal. Okay, this next part here is going to send an input signal to the control center of the whole operation, which in this case, the control center is the thermostat. Okay, that is what's controlling your air conditioning unit. That's what's telling the air conditioner when to come on and off. Okay, so the thermostat is the control center in this case. So the thermostat will sense that, okay, it's too hot in the house, and it's going to send an output signal to the effector. Okay, the effector is the structure that will come on, okay, or kick on and cause a response. So in this case, the effector is the air conditioning unit, right? It's the AC. So the air conditioning unit will kick on, right? That's what's going to be the response. AC comes on, and what's going to happen to the temperature? It's going to go back down. right? So the temperature will drop until it reaches 70 degrees Fahrenheit. And then we're stable, we're at the temperature we want, and the whole system will kick off, right? It turns off. Okay, so hopefully that helps illustrate the parts for you. Let me use a actual human body example. We can use body temperature again to go through this. So let's say it's really hot outside, right? And you go out there. The stimulus here is going to be increase in temperature, more specifically an increase in body temperature, right? Your body temperature is going to start to warm up, and a signal, right, is going to get sent to your brain by a receptor. So receptors found on the surface of your skin and all throughout your body. Okay, so we're just going to put the receptors are neurons, which are essentially nerve cells. Okay, they're going to sense this change in temperature outside and in the surface of our body, and then they're going to send an input signal to our control center. What is our control center? It's our brain, right? Our brain, or more specifically our central nervous system. Okay, so nerve cells will send a signal to our brain to tell us, hey, our body's starting to get too hot. This is not good, because if your body gets too hot, you can start to cause damage to your cells and damage to your tissues, right? And so your brain is going to send an output signal to your effector organs to try to help cool you off, okay? So one of the main effector organs that will be affected are going to be sweat glands, right? We'll send a signal to your sweat glands to tell them to produce sweat. So the response will be sweat production, right? Which we know will do what to the body temperature? It's going to decrease our body temperature, right? Which will help lower it and get it back to normal, help cool us down, and overall it will produce homeostasis within the body, okay? So a lot of times your body will do this, okay? It will cause a response to a stimulus until you have produced enough of whatever you need to in order to maintain that homeostasis, and then it will shut the whole production level off, okay? Now that type of response is what we call negative feedback. Your body will continually produce something until you have enough, until you have that stable internal environment, that stable homeostasis, and then the production will shut off or cease to exist until you get back out of homeostasis, right? Once you get out of homeostasis again, then the whole machinery, the whole production mechanism will come back on, and it will produce more till you get back to homeostasis, and then it'll shut back off, okay? Now keep in mind that there's also what we call positive feedback. Okay, now positive feedback is going to be very different. Most of the time, positive feedback mechanisms will take you out of homeostasis. Okay, they're going to take you away from homeostasis and put you in an abnormal situation. So, two examples of positive feedback would be during blood clotting process. Okay, if you're trying to form a blood clot to help prevent bleeding, that would be one. And obviously, if you get cut or damage a blood vessel, that's not a normal scenario. Your body is not in homeostasis at that point, right? There's something going on that's wrong. And another example of positive feedback is during childbirth. Okay, with positive feedback, again, this type of system is going to take you out of homeostasis. So when you start to produce something, the production of that is going to stimulate more production of that rather than shutting it off like you see in negative feedback. So like during childbirth, there's a hormone that's produced called oxytocin. Okay, oxytocin is what stimulates childbirth to start. And oxytocin, when it gets released, will start to stimulate uterine contractions. Okay, contractions, muscle contractions that help push the baby down towards the cervix to help get it out. And once the baby pushes down on the cervix, there are receptors in the cervix that will receive that sense of pressure and they will carry that signal to the brain to tell the brain to produce more oxytocin. Okay, when you produce more oxytocin, then that means the next contraction is going to be even stronger. It's going to push on the baby even harder. That's going to stimulate more oxytocin to get released, okay, which will cause the next contraction to be stronger. And so you'll produce more and more and more and more oxytocin, and the contractions will continually get stronger and stronger and stronger until you get the end result that you need or want, right? Which in this case is the birthing of the baby, getting the baby out of the body. Once the baby's out, then everything can go back to normal. Everything can go back to the homeostatic level that it was at before, okay? But positive feedback mechanisms are ones that take you out of homeostasis for a brief period of time to help produce the end result that you need to keep you safe, right? To keep you stable. And then once you get that end result, then your body can go back into homeostasis and everything will kind of get controlled by those negative feedback mechanisms again, okay? So make sure you go through homeostasis, through the parts of this, and that you understand this. Sometimes it can be a little tricky for students to understand the difference between negative feedback and positive feedback, but I do want you guys to know that, okay? I can't stress it enough. So if you have trouble with this or need more examples, please don't hesitate to let me know.